Ellie Johnson, and this is my Lab 3 presentation. So the purpose of this lab was to focus on the distance dependence concept of a magnetic field due to a small bar magnet. So we compared the experimental values that we got from looking at an app on your phone, the magnetometer app, and then we compared these values to the computational values of the distance dependence, which we predicted based on different things, a regression line, and that I created in Excel, and then we also used VPython to display this as well. I also use the equations for the on-axis and off-axis magnetic field in these ways, and we derived this from the Biot-Savart law. So the methods for this lab, in part 1, we used the app to see the magnetic field of a bar magnet and measured it where the magnetic field equaled 20, 70, 120, 170, and 200 microteslas. We identified the magnetic sensor in the phone, and then in part 2, we moved the phone until the magnetic field was, the net magnetic field equaled 100 microteslas and recorded the Y value of the field. Then we moved the phone so it was at a 45-degree angle from the bar magnet and accounted for the Y component by adding or subtracting the magnetic field in the Y direction of Earth from the magnetic field in the Y direction of the measured values. And I did this 3 times for each location to get 3 values of the D, and then compared the predicted and observed 45-degree measurements using the computational model. So some fundamental principles that I had to understand in order to do this lab were the Biot-Savart law, which basically has to do with the magnetic intensity at any point due to a current, and it's proportional to the current and inversely proportional to the distance from the point to the wire. And the general concepts of the magnetic fields were also important. So a region around the magnetic field or a moving electric charge is basically what the magnetic field is created by, and that's where the force of magnetism acts, and then the magnitude of this decreases as you are farther away from the magnet, and that is the formula for that. And the magnetic moment, which is shown in this diagram to the left, is basically just a quantity that determines the force that the magnet can exert on electric currents and the torque that the field will exert on it. So these are my final results. I got n equals negative 3.081 and that the magnetic moment mu is equal to 1.5. This is some of the data that I got experimentally. So the distance dependent of the magnetic field of a bar magnet, and I got the off-axis magnetic field equaling the following, and that the distance is equal to 0.284. This is the graph that I calculated based on this data, and it shows the correlation between the magnetic field and R, and how when you take the log of these, it ends up being a negative linear correlation with that equation to the right. These are some of the calculations that I use in order to apply this and get the predicted values. The distance dependence calculation is on top, and following is the magnetic moment calculation. So since V equals K to the R, KR to the N is exponential, the logarithmic graph showed a straight line in the previous slide. For my code, I was to create a program that calculated the dipole by using mu and R. So I created the magnet object and then got the mu of that and plugged that into the equation, and then used different distances and plug those into the equation later on. So as you can see below, I created all of my different objects to plug into the equation, and then I got my first 2 arrows at the bottom, and here are the rest of my arrows. So these are going to be my perpendicular arrows and then my 45-degree angle arrows. This is the graph that I created. So that's going to be the magnet, and the blue arrow is the on-axis, and then the orange arrows are the off-axis magnetic field. So the questions that I answered to summarize the lab. Thank you.